Carbon offsets is a concept developed under UNFCCC as part of the climate solutions, where people who have no choice but to emit or don't mind emitting. I like to travel, for example. I think travel is very important for cultural exchanges, for learning, for value additions to one's perspectives on life and so on. So I'm not sure if we can totally avoid it. So companies, governments needing to meet their emission targets can invest in emission reduction projects in developing countries. So carbon offsets include things like planting trees, renewable energy products. So each unit of CO2 you are inevitably emitting, let's say as a part of the corporation or a company, then you can pay someone to take out that unit of carbon somewhere else. Since it's a well-mixed, long-lasting gas, this could work, right? There are debates about whether this really works or whether this kind of encourages people to be not very careful about reducing their emissions and so on. Nonetheless, it's been in operation, and one can go look for whether it has been as successful as one would want. Certificates are obtained for payment of carbon offsets in this process. So when you fly, some airlines provide you the opportunity to give a tax to do carbon offsets, and even the American Geophysical Union, which likes to have these annual meetings with tens of thousands of people flying from everywhere to attend these meetings in person, do carbon offsets. So is that inevitable emission? One can debate about that. We will leave it there and look at what life cycle analysis means. We have already touched on this when we talked about how RCPs are generated. Basically, let's say we are looking at a bottle of water, which I don't have, fortunately. The bottle has a body and a cap and has water inside. So life cycle analysis basically looks at the raw materials that go into the bottle itself, into the cap, the transportation of the product in terms of the carbon emissions, and where the water is sourced, where it's bottled, and where all it is shipped. So the entire process tells you just what is the net carbon footprint of that particular bottle of water, for example. Okay, just because something says organic food, for example, you may feel good that it's organic and environmentally friendly, but if it's blueberry that's traveling from Chile to Washington DC, then it's adding a lot of carbon footprint along the way, so one has to be careful. So life cycle analysis basically tries to do that, and we will revisit this for bioenergy, for example, in terms of reporting as a part of the climate mitigation action under, let's say, Paris Agreement. Okay, so here are the resources, let's say biomass being used for material processing. There is product manufacturing involved, there is distribution involved, which should be going this way, but it's facing this way, haha, and it's being used as, let's say, energy, bioenergy at some place, and then the end of its life happens here in terms of the energy that's burned off, heat that's generated, and so on. So what is the net carbon footprint end to end in this system? That's the life cycle analysis. Not always easy to do, but more and more models are built now to do life cycle analysis of various things. So here is an example, figure 7.8 from the chapter, life cycle greenhouse gas balance of different conventional and advanced biofuels and the current state of technology. This is from International Energy Agency, a bit old, but you can find a later one. Based on a review by the International Energy Agency and United Nations Environmental Program of 60 life cycle analysis studies, this is looking at the assessment exclude emissions from indirect land use change. So tricky, life cycle analysis is never that easy. So basically that means if you're growing grains for biofuels, then there is an indirect land use change. You have either converted that land from something else to grow biofuel biomass, or you have converted it from food grains into biofuel biomass. So that is hard to account for in terms of the net addition of carbon footprint. So emission savings more than 100% are possible through the use of co-products. So the biomass sustainability can give you more than 100% emission saving, negative emissions. Bio-SG is biosynthetic gas. FAME is fatty acid methyl ester. HVO is hydrolyzed vegetation oil. So here it is looking at percentage emission reductions compared to fossil fuel. So when it's negative, actually it's doubtful that it's doing reduction. It may be adding. So for example, the algae biodiesel, which is still in the R&D and pilot state, at least at the time of this report, has some negative emission reductions. I hope that means not more than, no, that is, so that is actually worse than fossil fuel. Advanced biofuels, including gasoline replacements, diesel replacements, and natural gas replacements, which include butanol, cellulosic ethanol, HVO, the hydrolyzed vegetation oil, biodiesel, and biosynthetic gas. In the conventional biofuels, we have sugarcane ethanol, sugar beet ethanol, wheat ethanol, corn, rapeseed oil, palm oil, and biogas. And you can see all of them have various levels, some of them with more than 100% saving in emissions compared to fossil fuel. Okay, so that's what we get by doing life cycle analysis, a good handle on exactly what the end-to-end carbon footprint is. Looking at typical total carbon stock exchanges in million kilogram carbon per kilometer squared while converting to croplands, so above and below ground carbon is included in here. Examples are shown in terms of set aside land for these products, temperate grassland conversions, temperate forest conversions, tropical grasslands, and tropical forests. So these are carbon stock changes. So negative change means you are going to emit carbon. So there is pretty much no, there is one here, typical tropical grassland going to palm oil is actually putting in a plus 0.61. I should have, yes, this is the change. So positive change is sequestration. So sugarcane is obviously bad in terms of converting tropical forests into sugarcane plantations when it comes to change in carbon stock. Okay, this is why we need to do life cycle analysis. Just because palm oil is considered a bioenergy replacement for fossil fuel, it doesn't necessarily have a net carbon sequestration. It has to be tracked fully. This is a change in carbon stocks from land use change conversions, estimated payback periods when land is converted to bioenergy. So if you do a conversion and you produce bioenergy, how long does it take for it to become carbon neutral and then provide you the mitigation potential that is driving such a conversion? Again, looking at various land use changes going from tropical forests or degraded pasture lands and so on into above and below ground carbon stocks, degraded pasture, unburned sugarcane, change to soybean or cropland, cane ethanol payback, and so these are the number of years it would take for recovering the cost and making carbon neutrality and additional carbon sequestration. Lots of numbers, but these bold numbers here are the ones that have essential gain or net uptake from the atmosphere. So negative values denote a loss of stock on land emissions. So you can see these are the few positive numbers in the whole table. So one has to be obviously careful in making the choices in terms of biofuels as being beneficial. it's not always so evident. Typical emissions and savings factors for sugarcane bioethanol and soy biodiesel. Again, the same story in terms of biofuel production, default emission factor compared to gasoline and diesel, default direct emission reduction, avoided emissions, and avoided emissions per hectare of land. So this has to be done well, and obviously has to be done with life cycle analysis to make sure that in fact the land conversions are going to be net gain in terms of keeping carbon out of the atmosphere and buried in land. So replacing fossil fuels which are high emission with biofuels which are essentially meant to reduce emissions in a life cycle sense. That's important to remember. Not just that, for example, in Indonesia, I mentioned people setting fires purposely. How does El Nino forecast help? It can help a lot in terms of places which get hit drought can plan properly when the forecasts come several months ahead of time. Fishermen can plan properly because fisheries collapse in the eastern Pacific, for example, because the upwelling is reduced. The warming kills fish or drives away the fish that can move away, and so on. But if you're in Indonesia and El Nino brings wildfires there because of the droughts, and if some smart developer or somebody who wants to convert forests to palm oil is paying attention to El Nino forecasts and using that as an excuse to set fires and then blame it on El Nino, that's not a good thing. So, as a forecaster, obviously you want to strive for providing the most skillful forecasts, but does the life cycle analysis include the human action that is triggered by the forecast? It happens in weather derivatives, for example, trading in food grains based on weather forecasts, market forces, and so on, do affect the prices tremendously. People make money out of it, but that's because somebody else is paying a price in terms of the costs of food, increased expenses on food. We'll see later on that poor people, for example, spend a much larger fraction of their income on food than rich people. So they are living on the edge. Their vulnerability to such tactics are very high. So life cycle analysis at some point should include those kind of competitions between bioenergy, food security, water security, land use change, net carbon sequestration, and so on.